We are now ready to discuss in further detail the unsymmetrical bending. The unsymmetrical bending is defined as the bending caused by loads that are inclined to the principal planes of bending. One of the examples which we previously quoted was of a roof purlin, which, because of its inclination with the roof, are subjected to loads whose planes make angles with the principal axis of inertia of a section. We can also have unsymmetrical bending in symmetrical sections where the load is inclined to the axis of the symmetry. So in this cross section, we have, which in fact is a rectangular cross section, we have a moment inclined to the axis of symmetry. This moment has to be resolved into two components. One is vertical and another one horizontal. Each of these components produces flexure stresses that are normal to the cross section. Therefore, the resultant stress at any point would be equal to the algebraic sum of stresses at that point caused by each case considered separately. So in this equation, we have the moment mz contribution and moment my contribution both added to each other in order to get the resultant flexure stress. Please note, mz is the moment about z-axis and my is the moment about y-axis. Y and z are the coordinates of point that is measured from x, y, or z axis, which have origin at the centroid of the cross-sectional area. Iy and Iz are the principal moment of inertia calculated about y and z axes. In order to determine the inclination of our neutral axis, we can locate a point A on this neutral axis by condition that the neutral axis is the locus of points of zero stresses. So in this combined equation, we can put y and z equal to ya and za and make sigma equal to 0. From there, we can bring the y and z on one side and the rest of the variables on the other side. Y by z will be equal to tangent alpha. The components of m can be considered as mz equal to m cos theta and my equal to m sine theta. Plugging that in this equation, we will finally get tangent alpha is equal to Iz by Iy tangent theta. From this, we can see that unless Iz is equal to Iy or tangent theta equal to 0 or infinity, the neutral axis is not perpendicular to the load. Thus, the neutral axis is inclined from the z-axis in the same angular sense as the plane of the loading is from the y-axis. We can demonstrate this simple concept by the help of an example. So we are given a rectangular cross-section in this figure, which is subjected to a bending moment of m is equal to 12 kilonewton meter. The moment vector is at some inclination to the principal planes of bending. So we establish the axes. Z-axis is a horizontal axis, y is the vertical, and x is the longitudinal axis. We can decompose our moment vector with respect to z and y axes. So my will be equal to minus 4 by 5 times 12, which is minus 9.6 kilonewton meter, and mz will be 3 by 5 by 12, which will be equal to 7.2 kilonewton meter. In a similar manner, we can determine the moment of inertia about y and z axes. So Iy will be equal to zero point 0.4 times zero point 0.2 cubed by 12, i.e. 0.2667 in 10 to the power minus 3 meter 4, and Iz will be equal to zero point 0.2 times zero point 0.4 cubed by 12, which will give us 1.067 into 10 to the power minus 3 meter 4. Now, using the combined stress equation, we can determine the stresses at point B, C, D, and E. The stress at B is equal to 2.25 megapascal, at C is minus 4.95 megapascals, at D is minus 2.25 megapascals, and at E is equal to 4.95 megapascals. We have followed the right-hand rule in order to establish the signs of moment. As per our assigned axes, my is negative and mz is positive. In a similar manner, we will have y and z's put either positive or negative depending which corner we are corresponding to our assigned axes. We can draw the corresponding stresses, and from there we can locate the neutral axis. We can also use the formula which we determined, tangent alpha is equal to Iz by Iy tangent theta, and get our orientation of the neutral axis. The orientation comes out to be at minus 79.4 degrees. We can also determine the neutral axis based on the proportion of stresses along different edges. Like for example, along BC, we can use similarity of triangle as 2.25 by z is equal to 4.95 by zero point 0.2 minus z, where 2.25 is sigma b and 4.95 is the stress at C. From here, we will get Z value equal to 0.0625 meter. We can do the same exercise to find our distance y. And from there, we can work out our inclination alpha.